essentially to speak about some work that was done over this year, 2020, and also with the motivation to try and find some collaboration, work for the future. And so Gonzalo and Diego Rubiera Garcia are working also on Thinshells, but related more to the Palatini formalism, which is fantastic because that is really virgin territory. Nothing has been done except for a few papers done by Gonzalo and also by Diego this year, in fact, about Thinshells in the Palatini formalism. So I decided to speak about, well, a paper, maybe two papers, but I have a few, well, in fact, 3 or 4 papers that I'd like to share. Hopefully, maybe not more. But what is the motivation to go into Thinshells and also the so-called Thinshell wormholes? Okay. So also Gonzalo mentioned that this is a very informal conversation. I didn't prepare a PowerPoint. I was on and off well yesterday, and there were some fantastic talks, very well organized. Mine is not organized. Mine is really informal. Okay, so it's more of a dialogue with you. If you have any questions, any doubts, so please feel free. So it's more improvising, okay, about what exactly we do with Thinshells and what we do with the so-called applications to wormholes, okay. Okay, so much work has been done on Thinshells, okay, the so-called Thinshell formalisms dating back to the 20s, okay. So people were really working on these so-called cut and paste procedures and trying to paste different spacetimes, and there's a lot of work in the 20s and the 30s by Singe and Darmois and Langsos and other people as well. But only in the 1960s, I think, late 50s and 60s, did Werner Israel come up with 2 seminal papers, which were really fantastic papers, and all the modern work done with Thinshells based on his formalism. Okay, so it's basically called the Israel or the Darmois Israel formalism, for short, Thinshell formalism. So basically, in the 20s and the 30s, people were trying to match metrics, the metric functions, and very, very specific cases like Singe also. Singe in the 30s also had these very specific matching conditions. So when you match different spacetimes, which we'll see in a while, there's different ways to do it, okay? But the most general way is through the so-called Israel or the Darmois Israel formalism, where what is matched, what must be continuous is the line element, okay? So if you have 2 line elements, it's the so-called line element that must be matched and must be continuous at the matching interface, okay? And that implies that the metric functions can be discontinuous as the space-time coordinates, okay? So much simplified work takes into account that one works with the same coordinates in both spacetimes, and what people do is just match the metric functions. That's a very specific way to do it, okay? So Israel came up with a very generic way with different different space-time coordinates in these different regions of space-time, and I reiterate that it's the line element that must be continuous. Okay, so applied to wormholes. Well, one can apply this to a whole class of solutions, and of course, one can also do this with stars. And the Oppenheimer-Snyder solution of 1939 also uses a specific matching condition, and one can also find all these matching conditions with star solutions matched to exterior Schwarzschild solutions or vacuum solutions. So there's a whole class of matchings that one can do. Now, apply to wormholes. So I'd like to give also a brief outline. I don't know if everybody in the audience knows about wormholes. So I'd like to just speak about 5 minutes. Why is it so interesting to apply these Thinshell formalisms to traversable wormholes? Okay, so well, wormholes are very interesting compact objects. Okay. It's not mainstream, of course, but it has a lot of interesting and fun physics involved. It's got a lot of, I mean, one can really stretch all your theories when you consider the so-called exotic spacetimes. Okay, you have closed time-like curves. When you go into wormholes, you have to start thinking about the nature of time, because they can be manipulated to generate time machines. They violate the so-called energy conditions, okay, which were really imposed to be satisfied. Well, for instance, for wormholes, a generic feature is that the null energy condition must be violated, okay? Many people in the literature say that a specific ingredient of wormholes is that you need negative energy densities. That is not the fundamental ingredient, because one can have positive energy densities. What you need at the throat, which is a minimum radius, is that you need a negative radial pressure. So you have a radial tension, which is positive, or the radial tension is negative, okay? And then when you take into account the embedding diagrams, where one shows, for instance, that wormhole shape, the tunnel-like shape, that is the fundamental ingredient in wormhole physics, because you need that so-called flaring out condition, okay? And you can find this in many textbooks, in the Gravitation by Morris and Wheeler and Misner, okay, and many textbooks when one can find these so-called embedding diagrams. And then when one takes into account that you need a minimum radius, okay, so you have a minimum radius, the first derivative must be null, and then the second derivative of the lift function relative to the radial function must be positive. And this is the fundamental ingredient, okay? That's the so-called flaring out condition. I'm just speaking out with no formula, but just to try to motivate why we go into Thinshell wormholes. So this so-called flaring out condition, when you apply it to the Einstein field equation, that shows you specifically that the null energy condition is violated at the throat. So the null energy condition for a steady case is rho, the energy density, plus the radial pressure must be negative, okay? That is the fundamental ingredient to have wormhole solutions. So when people start speaking about the violation of these energy conditions, the null, the weak, and the strong, now at this moment we know that the strong energy condition is being violated due to the late-time cosmic acceleration, okay? So these energy conditions are not really laws, okay? They just principles, or they specific conditions that you impose on your energy momentum tensor to have a specific plausible energy momentum tensor, okay? So when people started saying, finding out that to have wormholes, the null energy condition is violated, and consequently all the other energy conditions are violated, the weak, the strong, the dominant, people started getting very, very anxious about this, you know, and so it was quite problematic, okay? Also depending on one's point of view, all right? So one can trace wormholes back to a paper by Ludwig Flamm in 1916, which is really amazing, okay? And that's the first incidence, or the first paper that I know of that specifically has incorporated a wormhole solution. Of course, Flamm wasn't looking for wormhole solutions. What he was trying to do was trying to work with the interior coordinates of the Schwarzschild solution. Schwarzschild had two very great papers back in 1916. First, the vacuum solution, and then also the interior solution, and that was quite confusing. So Flamm was trying to demystify that solution, and he was applying all these coordinate changes. Okay, so when you apply these coordinate changes, you sometimes double cover regions. Okay. And when you double cover regions, one has this matching condition, okay, and which is matched at some specific radius, minimum radius. And it's in that sense that one can, with hindsight, see that these coordinate transformations that Ludwig Flamm in 1916 was doing really speaks about a traversable wormhole, okay? So that's the first instance that these solutions appear. One can go to 1935, where Einstein and Rosen were playing around with creating a geometric model for particles, and they came up with the so-called Einstein-Rosen bridge. Okay, so if you have the Schwarzschild solution, it's one can see this very well with the Penrose diagrams. Okay, you have the white hole solution and you have the black hole solution, and then the transition from the white hole to the black hole is an Einstein-Rosen bridge. Okay, but that's a non-traversable wormhole. So one finds also in the literature and also in the films, where people travel through these so-called tunnels, and they call them Einstein-Rosen bridges. Okay, they're non-traversable because they essentially black hole solutions. Okay, so that is 1935, the so-called Einstein-Rosen bridge. And then one goes into the 1950s, where John Wheeler was getting really interested in GR, and he came up with this beautiful theory, that's the unification of theories, but not in a simply connected spacetime, but in a multiple connected spacetime, where one couples the Maxwell equations to the Einstein equations, and there's no sources for these fields, okay? Because these so-called fields are tunnels, okay, in space-time. And he called these solutions the Geon solutions, okay? So this is the first time that these wormhole solutions really appear, okay, in the literature. And in fact, Wheeler called them wormholes. There's a nice paper by Misner and Wheeler in 1958. I think it's called the already unified theory, okay, where you don't need more unification. All you need is just the Einstein field equations and the Maxwell equations, but in a multiple connected space-time, and you have all these unified theories. One has fields, one has electromagnetic fields without sources, So these mantras came about, mass without mass, charge without charge, it was really fascinating. So a lot of work was done there in the 50s and the 60s on the so-called Geon solution. So Geon is the gravitational entity, the gravitational electromagnetic entity, okay? But then it was found that they were unstable, and people still work on these so-called Geon solutions. Going through a bit further on, in the 70s, there were two nice solutions by Homer Ellis. He called these wormhole solutions a drain hole. And a nice paper appears by Ellis in 72. And also Bronnikov. Bronnikov also found a very similar solution to Ellis's, but using scalar fields. So these two solutions date back to 1972, 1973. And then the field lay dormant until 1986, 88, 86, when Carl Sagan wrote his book, The Contact, where he wanted the heroine traveling through a tunnel-like solution, going up, very far away in space-time. And he was using a black hole. And he sent his manuscript to Kip Thorne to see if the physics was correct. And of course, one cannot, a black hole cannot be used as a two-way travel, okay? It's just a one-way. You go inside and you stay there. So Thorne came up with his fantastic solutions, He tried to see how to find a two-way travel solution. And then that gave origin to the seminal paper of 1988, where wormholes really became mainstream. I mean, many people started working on this, And I'd like to focus on Matt Fisser. Matt Fisser also started getting very interested on these wormhole solutions, and he was the first person who started applying thin shells. He was the first person to start applying the thin shell formalism to wormholes, essentially because they were much easier to work with, okay? And also that one could minimize the so-called violations of the energy conditions, okay? Because Thorne and Morris, Kip Thorne and Michael Morris, Morris was his student, was Thorne's student, and its seminal paper is by both authors. They found out exactly what I mentioned before, that you needed the violation of the null energy condition, okay? Rho plus PR, the energy density plus the radial pressure, must be negative, okay? So that's what essentially violates the null energy condition. So in order to try to minimize these violations, Fisser found that one can use the Thinshell formalism and construct very simple wormhole solutions, kind of portals, you know. The Form 2010, I think they're using these portals, right? So what you have is essentially these polyhedral or cubic or quadratic or rectangular wormholes, where you have all these, we have two spacetimes, very simple spacetimes, such as Minkowski spacetimes, but matched together, okay, in these polyhedral forms, okay? So all the energy, all the negative energies, all the matter that violates the energy conditions are really constrained at the junction interfaces, and that really minimizes the violations of the energy conditions. So that is one reason, essentially, why these thin shell constructs came into play and became really mainstream. Okay. So I'd like to show you two papers, well, at least one paper, which is quite pedagogical and shows you all the formalism behind the thin shell formalism, and a lot of papers have come out. There was a very nice paper, which I'll have, if I have time, I will also show it, by Matt Fisser and Eric Poisson in 1996, where they also used the thin shell formalism to study dynamic solutions and the stability around linearized perturbations. Okay, so let me show you with a specific example exactly what you do. Okay, what you do here. Are there any questions until now? No. Okay. Okay, so so this paper came out in March. It was published a few months later, and it's basically about Blackbounce traversable wormholes using the thin shell formalism. Okay, so these Blackbounce solutions, geometries, were essentially they were conceived by Matt Fisser about 2 years ago, and by his student Alex Simpson. In fact, and then we found out that also other people had already found similar solutions, like Coletu from Rustu Coletu from Romania, and also other people. But let me show you exactly what these are. So yeah, sorry. So here's the metric for the so-called Blackbounce spacetime. You have this, well, the radial coordinate is the u, so it varies from -infinity to +infinity. Here we have the time coordinate, and this part of here can be thought of as the area, the area of a sphere. Okay, so this is the original metric that was worked out by Matt and Alex, but we found it much easier to go into Schwarzschild coordinates, because it's much simpler, and one can also compare to the Schwarzschild solution. Okay, so one can transform this line element to this one by taking into account this coordinate change. Okay, very similar to what Flum was doing back in 1916. Okay, so if you go from this solution, line element 2 to 1, you double cover two regions. Okay, and these two regions are matched at u is equal to 0. Okay, and that's the minimum radius, which also can be thought as a wormhole. Okay, so if you take into account this perimeter equal to 0, okay, that takes you to the Schwarzschild solution. So one has a one perimeter extension of the Schwarzschild coordinates. Okay, and here's the and for instance the area of a two-sphere. So now R, if you take into account this coordinate change, now R, the radial coordinate, ranges from A to +infinity. We consider A as positive. Okay, so take into account this line element. Okay, so basically this is the line element that we'll take, and this is what is called the Blackbounce geometry, because it describes essentially a regular black hole solution. Okay, you can look at Matt's paper, Matt Fisser and Alex. They somewhere here referenced, and well, in fact, yeah, we are 66 and 8. You can have a look at those original papers. Okay, so these things were applied to many solutions. The Thinshell. Now, essentially, what does the Thinshell formalism tell you? Okay, taking into account the Israel formalism. Okay, so we have two bulk spacetimes. Okay, so we have two spacetimes. One can take two copies of these. Of this line element, of this geometry, and then glue it together at a junction interface, okay? So this junction interface, so M plus, M minus, we have two copies of the solution. We can call plus the exterior solution minus the interior solution, and it's matched at a boundary surface, okay? Or a, and that is what we call the sigma or the delta M, okay? So that's the interface where you match the two solutions, okay? So here we just describe plus and minus as the exterior and the interior solutions. Well, this is the energy momentum tensor for this space-time. We suppress the plus and minus not to overload the notation. And here we see indeed that the null energy condition is violated, okay? So this, I just saw a typo over here. So this must be square root. I apologize for this. This completely missed us. But this violates the null energy condition, okay, throughout space-time. So what we do, in fact, is match these two solutions, okay, and construct these Thinshell formalisms, okay? So here is a line element for the interface, for the junction interface. I won't go much into details. We have here the intrinsic metric, which is the metric on the junction interface. We have the scalar product of the basis vectors, which are tangent to the junction interface. But in fact, what will be needed will be the fall velocity of an observer who is co-moving along with the surface interface, okay? So one can calculate this quite easily. Well, it's quite time-consuming, but it's really straightforward. We have here the normal vector. Normal vector is a normal which is normal to the junction interface, okay? We have, for these two space-times, this one, over here, we have two normals. So we assume that the normal points from the minus, M minus to plus minus, and that is given by this formula over here. Okay, one can just use the definition of the normal, take into account this function, this parametric equation, use the definition to find these equations, or simply one can use this contraction of the fall velocity and the normal, and one can just play around with this. Using these two conditions, one can also find the normal. So the plus sign is for the normal that points outwards of the exterior spacetime, and the minus will be the normal that points out from the interior spacetime, okay? So this will be important. Why? Because this will permit us to calculate the extrinsic curvature, or the second fundamental form, okay? One can do this in several ways. One can play around with the definitions, okay? Here we have the orthonormal basis on the junction interface, and we can play around with this to calculate the extrinsic curvatures. But it's quite pedagogical also that you can just reorganize this definition and write it in this way by equation 14, and it's really straightforward to find these components, okay? So the plus and the minus are the extrinsic curvatures on the exterior and the interior spacetime along the junction interface, okay? Okay, so once you have these, so essentially I mean, if you look back into the papers of the 1930s, they consider that this second fundamental form is continuous, and what they do essentially is just equate the metric functions, okay, along the junction interface, and also the first derivatives to find specific, very simplified junction conditions, okay. But once again, that is not the general form or general way to find these junction conditions, okay? Anyway, so now that we have the extrinsic curvatures, okay, here, which is defined in terms of the normal, well, we can go to the Einstein field equation on the junction interface, okay, on the Thinshell. So one can play around with the Einstein field equation, and one can deduce the so-called Langsource equations. The Langsource equations are the Einstein field equations, which are applied on the junction interface. Okay, so this surface energy, the surface stress is given by sigma, which is the energy density along the surface. We have a big P here, the calligraphic P, which is the surface pressure. And one can see easily that it's given in terms of the discontinuity. So this small kappa is defined as the, here it is. So it's the jump of the extrinsic curvatures along the junction interface, okay? So it's the discontinuity, okay? And one can find now the exact form for the surface stresses, which is this one and this one. So you see that the sigma, the surface energy density, is always negative because you have the square root here and you have a plus sign and a square root. So this term here is positive and we have a negative surface energy density, okay? So for these constructions, at least for these thin shells that are constructed in this way, we always have a violation, at least a violation of the weak energy condition, okay? Because the surface energy density is negative, all right? Okay, so one can see that if you consider symmetric spacetimes where the perimeters, let me just go back to the metric. If they're symmetric, where the m minus is equal to the m plus as the a also, it does simplify extremely, okay? So this is equal to that. I mean, so it's really a very simplified case. So we're just considering that they're not symmetric, that they're asymmetric, okay? What will be very useful later on will be to define the surface mass of the thin shell, which is given by this condition over here, okay? Which is very simple. It's the mass of the the circumference, okay? Where sigma is given by equation 20, which is the surface energy density. Okay, so now going into the subtle parts, okay? Because they're quite subtle in GR, and they must be even more subtle using modified gravity. So this is where I was thinking of speaking with Gonzalo and also Diego. Because these are the conditions that one should really take into account to generalize their formalism in the Palatini formalism, okay? So in fact, let's take into account the Gauss equations and the Gaudesi. What are these? So they're purely mathematical statements, okay, about how the Einstein tensor behaves along on the thin shell. So one can show quite simply, in fact, that this condition over here is given in terms of the conditions that are applied on the thin shell, okay? The extrinsic curvature, and here we have the 3 curvature on the thin shell, all right? And one can show through the Einstein equation that this condition is valid. So this is the so-called, it's got several names, okay? It's got the, it's called the first contracted Gauss-Gaudesi equation. It's also it's often referred to the Hamiltonian constraints, and there's also other names. Okay, so this is a very important geometric condition that appears in GR. Okay, now one equation which will be very important in modified gravity will be the second, or the Gaudesi minority equation, okay? So it's also called the second contracted Gauss-Gaudesi equation, or the ADM constraint, or the momentum constraint. There's many names, but essentially it gives you some conditions when you contract your Einstein tensor to the vector basis on the thin shell and the normal. So that gives you this constraint, this purely mathematical constraint on the right hand side by equation 25. Okay, so if you take into account the Einstein field equations or the Langsource equations, that will give you this important condition, okay, which is equation 26. And note that this will be extremely important for the conservation equation. Okay, the conservation of the energy momentum equation, which we will see later on. Now, have a look at equation 27. So equation 27 is written out explicitly, taking into account our metric. So you have this condition over here. You have the sum. Okay. Of course, this is the this square bracket is given by the discontinuity at the thin shell. So you see that this, generically, for most of the geometries that are taken into account in the literature, for instance, have a look at the Schwarzschild spacetime. Of course, it's vacuum, but the Rise, the Nordstrom, and in fact, many of the well, the great majority of the spacetimes taken in the literature take into account that this condition is 0, okay? And that gives you essentially black hole solutions, all right? But for a generic spacetime, it's not 0, okay? So when this right-hand side is non-zero, it gives you a flux term, which is given by this this chi given in equation 28, okay? Which, taken into account our metric, is given by this equation 29, okay? So if you take into account the covariant derivative at the thin shell of the surface stresses, this will give you the conservation quantity given by this here, where we've just redefined the A as the surface area of the thin shell. And we see that there's an extra term that appears here, which is due to this flux term, okay? So when this flux term is null, is 0, we have the normal conservation, the standard conservation of the energy momentum tensor on the thin shell. Generically, it's non-zero, okay? So you have a flux which impinges. So this is thought of physically by a flux energy term that hits the thin shell either from the inside or the outside, okay? Essentially this, well, this conservation equation over here, well, to give you just the physical background, you know, it's the, this term here is given by the work done by the external forces. It's somewhere over here. Oh, here we are. And, well, in fact, I'm sorry. This is the first term. Well, the first term is given by the variation of the internal energy of the shell. And the second term is given by the work done by the shell's internal forces, okay? And, of course, this term encodes, here it is, incorporates the flux term, okay? Which is the work done by the external forces. So we have here this, well, this equation 31 can be given as equation 32, okay? So basically, we have here these equations. We have here the sigma and the p, and we have here the conservation equation, okay, or in this case the non-conservation equation. Okay, now to I don't have much time, so I will just finish off and then the formal discussion, and then show you exactly how to find specific solutions. Okay, so now to there's many ways that one can do the stability of these thin shells. A very simple way is through the so-called linearized stability analysis. Okay, so basically this equation over here of the energy momentum tensor, the sigma this can be reorganized and written as this equation, okay, which can give you a kind of a kinetic term, and here we have this potential, which is given in terms of this, with many redefinitions to simplify the notation, okay? So this comes from the surface energy tensor, can be reorganized here. And now what is usually done in the literature, okay, to find the stability analysis, let me go back now to the first paper to show you what is done. I'll try to be quite quick. This is a paper by Matt and Eric Poisson, okay, dates back in 1995. So just very quickly, so what they do is exactly what we did, but for the Schwarzschild metric, okay? Let me show you where it is. They have here all the formalism, okay, we have the extrinsic curvature. They don't have here, but in fact, this is the Schwarzschild solution, okay? So what they do here, so here's the surface stresses, okay? And here we have the conservation equation. As there's no flux term, that's 0. It's 0 over here. So what is usually done is basically they take into account this perimeter, okay, this beta perimeter. So in standard fluid dynamics, this is considered the speed of sound. But as we use in now exotic matter, this cannot be really considered the speed of sound. And there's a very nice, if you want to read the discussion, it's over here in the conclusion about the interpretation of this perimeter, okay? it's in the conclusion. So it cannot be naively taken or defined as the speed of sound. So, but what is really done by the majority of the papers until 2012, 2013, is that you take into account this perimeter. Okay, you linearize the potential. Okay, you have the conservation equation. Okay, like we have here. Let me just show you, like we have over here, but given in different coordinates. Okay, and you just take into account the potential and linearize it until second order. Okay, so the first term is 0, the second term is 0. And only the second term, the third term will be non-zero, okay? So you have a minimum, and this must be positive, okay, to be stable, all right? And then, taking into account these two equations, the sigma and the p, you take into account this perimeter, the speed of sound, and then you find the stability regions of the speed of sound in terms of the distance. Okay, so this is a standard way of doing this the so-called linearized stability analysis. Okay, what we did in 2012 was do it in a different way. So we rewrite all our equations in terms of the potential. Okay, not vice versa, as is done here. So here one takes into account the potential, where you've defined it in this way, okay, and then you play around with the surface stresses, and then you rewrite the potential in terms of the surface stresses. Okay, here we are. What we do here is a reverse philosophy. So we rewrite all our relevant surface stresses, also the flux term, in terms of the perimeters of the theory, but also the potential. Okay, and then we do the exact same thing that was done in the first Poisson paper. We linearize the potential to third order, and we arrive at this equation 41, where to be stable, this second derivative must be positive. Okay, so now we rewrite the sigma. Okay, the sigma in terms of the mass of the thin shell. Okay, given by these equations. So here we're looking for conditions. What are the conditions of the surface stresses on the thin shell that will stabilize the solution? Okay, so now we're not taking into account that so-called problematic perimeter, the beta, which is the tentatively called the speed of sound, but now we're just imposing some conditions on the matter. And what are the conditions that we have to impose on the matter, the surface stresses on the thin shell, to make the solution stable? Okay, so for the solution to be stable, this potential must be this second derivative, must be positive. Okay, so now we take into account the time dependent solutions. Okay, and find them at a static solution. Okay. So we just use this original solution, sigma, in terms of the mass. We find the second derivative. Okay, we have this complicated equation over here. As we have now two conditions, we also have the flux term. We also have to find what are the conditions imposed on the flux term. So we have two independent conditions, because now we have a flux term, and the master equations applied at a static, stable solution are given by these two equations here. This equation, okay, when the potential must be, when the second derivative of the potential must be positive, we have this stability condition, okay, and we also have another condition that's imposed on the flux term, which is quite complicated. So the two master equations are this one, this inequality, and this inequality. Okay, so now we just play around with this. Okay, we play around and we consider specific solutions. Okay, when the flux term is 0, and we find specific solutions. Okay, this is the Schwarzschild solution. Now one can just go ahead and we can just play around with this. Okay, one can consider that the masses are 0. We have non-symmetric A's, and now it's just playing around. Okay, so essentially this is what is done. Okay. Let me show you a case very quickly. I don't know if I have time for this, but a second paper that came out in August, I think, yeah, that we play around with a much simpler solution, okay? We have, let me show you the line element, which is this thing over here. It's a kind of, it's also a regular black hole solution, but it's asymptotically Minkowski at the core, and that's given by the suppression factor over here, okay? So at the core, we don't have a singularity, it's Minkowski, okay, at the core. Let me just show you that, look, as these metric functions are inversely proportional, so this GTT is equal to 1 over GRR, that tells you that the TRR, that is the radial pressure, plus the TTT, the energy density must be 0, okay? So that tells you precisely, let me just show you. Well, here it is, okay? So it's 0, okay? And that tells you that the flux term, let me go back to the original solution, the flux term, sorry, here we are, that this flux term is 0. So there's no flux term. So that tells you that for this solution, here it's better explained how you get to the four velocities, the normal, the extrinsic curvatures. Yeah, we have really pedagogical outline how to find these specific terms if you're interested. Okay, it's very, very pedagogical. But now we have here the long-distance equation, of course. Yeah, you have the surface stresses. And here we have the flux term, which is 0, okay? So this takes you to a much simpler conservation equation, which is given by 231. So for this case, it's much simpler to find the stability analysis because you only have one condition, all right? Which is now the master equation. You do the exact same thing, and we only have this condition over here. We don't have the flux term. And now one can play around with the perimeter range, okay? One can consider specific cases for the mass, for the A's, etc. Okay? Well, I'll stop here, okay? I hope that I wasn't too confusing. And I hope that you found this clarifying and that it wasn't, well, in fact, too boring. So thank you very much, okay?
Thank you, Francisco.
Yep.
So very nice talk. I enjoyed very much all the details and the nice historical introduction was very interesting. So now we have some questions in the audience. It has been a parallel debate here on the meaning of Blackbounce. So can you explain what Blackbounce means?
Oh, okay. So let me just go. Okay, let me just go to the paper. Okay, so it wasn't really. I'm sorry, I didn't in fact tell you exactly what it was. Okay, what a Blackbounce was. So in fact, it's a space-time. A space-time that when you have a time-dependent solution, one can work with the null coordinates here, and one can see that as an infalling solution, okay, as it reaches the core, it bounces back out, okay. So that is, in fact, it's a Blackbounce because it's a black hole that's bouncing, okay. I mean, I don't really know how to explain it better, okay. Let me give you two references: the 67 and 68, okay, of the paper, which tells you essentially how this is done, okay? So it's really transparent if you take into account the Vardier space-time, and one finds out that you do have these bounces, okay? So as they reach the core, it bounces back out, okay? So it doesn't collapse to the singularity because there's no singularity. So you have one can also see this intuitively because as the violation of the energy conditions at that core, okay. So the geometry will be repulsive, okay. So as it's collapsing, it reaches that region and then it bounces back out, okay. So in a certain sense, I mean that's the way that I see it intuitively, okay.
Okay, so Francisco, we would say that it bounces not back, but forward, right?
But sorry.
when the collapsing matter bounces forward, not backwards.
Oh, yes, yes, yeah, of course.
Because it
Bounces
is
forward.
growing. The space-time again is growing, and since you are inside the
Yes, yes, exactly, 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 exactly.
go in other direction.
Forward, exactly.
Okay. So there is someone raising the hand, but there were a few more questions before. So Andrea, please wait. So
Gonzalo,
see? Yes.
there's a lot of people. It's very hard. It's very hard to understand.
I didn't understand. Please repeat.
Sorry, I don't know if Gonzalo. Okay, Gonzalo, did you?
What's the question? Sorry.
Yes.
I didn't get the question.
We're having trouble. Francisco.
Okay. So.
What's the question?
Okay. Is it all right now?
Oh, it's much better. It's much better.
I can hear my echo. Okay, but if it's better. So Gonzalo, should I? Okay, there's okay.
Okay, so what's the question? Sorry. Okay, I've turned off my mic.
Okay.
So,
No.
is there echo now?
No echo. Now it's much better.
Okay, so Albert Petrov was asking if can wormhole metrics display singularities at any point?
Wormhole spacetimes at any point.
If they can
can wormhole spacetimes have singularities at any point? Is that the question? Sorry.
Yes, that's the question.
Okay, so we assume so Albert Petrov. So we assume that in wormholes, okay, that there's no singularities, okay. So we assume that the metric is regular everywhere, okay. Whilst it'll be very problematic, okay. So a wormhole spacetime can be seen well through different ways, but the most simplest way is that it's a tunnel. It's got a minimum radius, okay, which is regular. One can also consider that it's asymptotically flat at infinity, of course, you know. So it's regular everywhere. And how do you do that? One considers that the redshift function, that's a function that appears in your GTT metric component must be regular and finite everywhere. Okay, so it must not. So your GTT, your metric function GTT must not be zero. It must be finite, non-zero in fact. So you don't have horizons, and that also tells you that the space-time is also regular. Okay, and one can see that if you take into account the Kretschmann's curvature invariance and the curvature scalar, because usually it's they're given in terms of 1 over r, right? 1 over r, r is the radial coordinate, but here the minimum value for the radial coordinate is finite, okay? Is r0, so it never diverges. So we impose that for wormholes, there's the wormhole geometries are regular everywhere. There's no singularities that appear. Okay, Alberto? I don't know if I was clear.
There is another question by Flavio. He was saying that concerning the metric endowed with an asymptotic Minkowski core, the solution that you propose with an internal Minkowski,
yes.
What does it imply for the Buchdahl theorem?
Oh, that's a good question. That's a good. So let's go there. Yeah. So if you have, so that'll give you. So as your metric, as your metric, well, now is not Minkowski. It depends on the suppression. So that'll give you different bounds, okay? Different Buchtal bounds. I'm not sure if that has been done, okay? But my first gut feeling will be that you will have different Buchtal bounds depending on the suppression parameter, okay? I don't know if it's done in Matt's paper, but you can have a look at that, okay? If it's not done, that should be done, okay? So because that's a very good question.
Hi, Francisco. So concerning the formation of these objects, do you have any hints about it? Because usually for very compact objects, people don't describe a reasonable form then dynamically in some scenarios.
Caio, right? Caio, I'm sorry, I didn't get your question. It goes on and off. In my phones, it went on and off. I didn't really get your question. Sorry.
Okay, well, I will type the question.
Yes. Okay, let me have a look. About the formation of these objects, is there any model to study it, like in dynamical collapse? About the formation of the, that's a good question. Okay, how do you study the formation of wormholes? Okay, that's a very important question. Diego is saying about linear stability against small perturbations, but are you, Caio, are you thinking about how do these objects form? How do these wormhole solutions form? Is that what your question is? Because you say like in dynamic collapse, you know, to form. Yeah, to form. So your question is how do these wormhole solutions form, right? Okay, fantastic. Very good question. Nobody knows, okay? Nobody knows. Let me tell you that, well, to have wormhole solutions is very complicated. First of all, wormholes are multiply connected spacetimes, okay? One can compare it like a cup, which is a normal cup, okay? This bottle is a simply connected spacetime. A cup with a handle is a multiply connected spacetime. So to form wormholes, you need a multiply connected spacetime. So you have to, in some certain sense, rip the fabric of spacetime in two places and then join them together, okay? So you have topology change. You have a change in topology, which is an extremely troubling issue, okay? In quantum gravity, in quantum mechanics, I mean, everywhere, okay? So nobody knows exactly how to form these wormholes, okay? First of all, due to this topology, this change in topology, okay? And if you go into the literature back, I mean, dating from the late 50s all the way to the present time, even the definition of a change in topology is not very well understood, okay? Because there's many ways to do it, okay? So first of all, to have a wormhole, you need to have a change of topology, and it's not really known how to do that, okay? So that's a very problematic issue, and that's one reason why people say that these wormhole solutions are extremely pedagogical objects, because they really stretch your theory, okay? For instance, how do they form? I don't. Well, Diego has an answer. So following Caio's question, perhaps one should consider dynamical scenarios where you track the proper time of formation of the bounds as compared to the time. Yeah, okay, but this is I think that's Diego. This is a different question, right? Because what we speak here about is how do these solutions form, right? So, so Caio, that's a very relevant question, okay? And I don't think that anybody knows, okay, how they formed, okay?
Okay, Adrian, do you have anything else to say?
Yes. So I actually wanted to ask. There is echo again, right?
Sorry, there's a.
Okay, so I'll go. My problem is that I don't get what is the difference between a Blackbounce and a wormhole.
Oh, what is the difference between a Blackbounce and a wormhole?
Yes.
Yeah. Okay, let me have a look. Yeah, I mean, a Blackbounce, originally a Blackbounce is not a wormhole, okay? It's just a space-time where you have the solutions, well, that are bouncing, right? Okay, so there's no wormholes there, all right? Now one can formally use these Blackbounce black hole solutions, okay, to construct these Blackbounce wormhole solutions, okay, through the Thinshell formalism, all right, as is done in the in the Schwarzschild solution, okay. So in the Schwarzschild solution, so there's no relationship between a traversable wormhole and the Schwarzschild solution, but one can build a wormhole through the Schwarzschild solution, through the cut and paste procedure, where you cut the inside, I mean a certain region of the Schwarzschild solution, okay, outside the horizon, and then you glue two space-times like that together, okay. So in that sense, formally, you have a Thinshell Schwarzschild wormhole, okay? So that doesn't tell you that the Schwarzschild solution was a wormhole. In the same sense as the Blackbounce regular black hole solution is not a wormhole solution, but you can use it, okay, to construct these wormhole solutions in a very analogous way. Yes, that's exactly what I'm saying. I mean, that's what Fisher and Simpson are saying, that you have this infoliant matter which bounces out. Okay, so they're regular black hole solutions. Yes. So in that sense, that there is a minimum of the area function in Blackbounce spacetimes. So, Adria, so what you're saying is that if you have a minimum, you also have a wormhole. Is that what you're trying to say?
So I was trying to reason. I guess if you have a minimum, but you can prove that you only have one region, and covered with your So for having a wormhole, you need a minimum, and then to one at each side.
Yeah. Yeah, that's a good question. I mean, so what you have is, but the minimum that minimum is given by that perimeter, right? The perimeter of the Blackbounce. Yeah, I don't know, Adria. Okay, I don't know how to answer your question at this moment. Okay.
Okay.
But yeah, but that's a good question also, because if you have a minimum, you can, I mean, you can have a construction that will give you a kind of a wormhole solution if you have a double layer.
Exactly.
Think about it.
So at some point, if you only have one region, it's okay. But if you have like two regions, if you can traverse the place where you have the minimum, it looks like or not, might be a matter of interpretation.
Yeah, I see what you mean. I see what you mean. Okay. Let me try to get back to you. Okay, just one quick answer, because Diego says here, what about the number of horizons in your black bounces? In this solution, there's just one. Okay, I was going to show you another paper, but I didn't have time. But let me show you a third paper that came out in October, where you have these new black bounce geometries. So that's, so we have here all the different types. Okay, so the Fisser black hole solution, the Fisser black bounce solution is given by equation 8. Okay, we have here all the Penrose diagrams also given. Okay, over here we have, you can have a look at that. So this is the original black bounce, which we call the Simpson-Fisser black bounce spacetime, which I described. Okay, so we've constructed all these new solutions. We have multiple horizons. Okay, you can have 2, 3, 4. You can have n horizons. Okay, and you can see through the have a look at this paper. Have a look at the Penrose diagrams. Okay, let me just show you. Yeah, well, this is a bounce solution. But let me show you another one, which will give you over here. Well, this is also a black bounce solution, but over here we have several horizons. Okay, we have more complicated solutions, which have a look at this paper, because it answers your question quite well. Okay, that will give you different different horizons. Okay.
Okay, so Francisco, I think it's time to finish, because we have.
Okay, thank you very much.